Summer by Vivaldi. And we're going to get into our autumnal equinox soon. Vivaldi. And now we're going to meet at a river with the bow down. I play a Lion Healing Pretty Lever 40 harp, so I always need to check my levers. And then we're going to go into Racing Against the Sunset with Philip Wesley. And that was Philip Wesley, Racing Against the Sunset. Now to River Talk, and here we go on the equestrian trails.
Thank you so much, Kim. That was just beautiful.
Oh, thank you so much.
And I think we're at the point where it's about time to begin our meeting. Thanks again. It's always just lovely to have that harp music to start us off. And actually, we could hear it in the auditorium this time. I mean, this is like really cool. Anyway, welcome to all of the people that are here in the audience, and welcome to all of the people that are out there in Cyberland. This is the August meeting of Orange County Astronomers, and I am the current president, Barbara Toy, in case you don't recognize me. I know it's been a while. Before we get going on the meeting, there were a few things that I wanted to bring up because I'm not sure that we're in a position where they've actually been properly noted in the announcements. One is that we do actually have a social media coordinator at long last. We are very excited about this. His name is Rich Cormier. And you can see his contact information on the contact list and on the back of this astronomer. And I think we'll be seeing a lot more of him on our social media accounts. Anyway, we're really grateful to him for stepping up, and we're looking forward to what he's going to be able to do to give us a bigger presence in those arenas. Another point that we were just notified about today, the astrophysics group, which has been meeting at the Heritage Museum for years, actually is going to be changing its meeting location starting in September. So if any of you are interested in going to those meetings, check the website for the the new location, and it'll have instructions and everything on how to get there. Then the last point I wanted to make was, for those of you who are not aware, we've been experiencing a fire in the vicinity of our Anza site. Excuse me. It's called the Nixon Fire. Some of you may have seen stuff about it in the local papers even. It was quite sizable. For a very long time, it was not contained at all. It now is pretty much entirely contained. It's most active in very wild areas that are some distance from us. At its closest, it was about a half mile from our site. So when we keep asking people to be sure that they keep the weed growth and so on under control on our site. I mean, believe me, this is a very, very real concern out in that area. This is the second fire we've had out in that area in 2 years. And fortunately, though they came close to our site, they did not get to our site. When there is a fire in the area, the roads are generally closed because there's limited access and the emergency personnel need it. And electricity can be off. It was off for a period of time on our site. I understand now that the roads are open, have been reopened, and that electricity is back on. But you should definitely check, like with CAL FIRE, excuse me, if you're planning to go out there just to see if there's any change in the situation. Anyway, now things are looking a whole lot brighter than they did a week ago. We had to cancel basically the star party last week because we couldn't get there. Everything was closed, and we wouldn't have been able to see much anyway because smoke is not good for good optics at all, or for seeing things up in the sky. anyway, with that, I will turn this over to whoever is doing the announcements. Is Kyle doing the announcements? Yes, I see Kyle there. Take it away, Kyle.
All right. Here we go. Right. Welcome, new members. You can find your name badges on the whiteboard there in the meeting hall, either this month or next month, depending on when you joined. If you're currently attending the meetings remotely, after a couple months, those will just be mailed to your home address. Just an FYI that the coffee stand and snack stand is closed tonight, but it'll be back next meeting for the usual coffee, donuts, and water. Star parties, the next ANSA star party is currently scheduled for August 31st. Astrophysics will be meeting this month at the Heritage Museum, and they're moving next month. Beginners class will be September 6th at 7:30 online. The next board meeting is September 8th. You can check the website for all of the events. Just check the calendar tab, and it'll list the time, location for all of our upcoming events. Outreach events, Martin Christensen is the outreach coordinator. You can contact him at the email there, outreach@ocastronomers.org. And speaking of outreach program, we have some upcoming outreach events that have been scheduled for the beginning of the new school year. You can see a couple right there at the beginning, August 20th and September 7th. We need volunteers for all of these events. If you're willing to help out and bring your telescope out to these events, please contact Martin. The Orange County Astronomers Adopt Scope program is up and running. You can find more information on the website there, where you can see a sample adoption agreement and download current inventory. And there's some more information about how the program works on that tab. Our newsletter, Dave Fisher is the Serious Astronomers editor. Please contact him with any items of interest that you think might be interesting for the club members to read about. Things we generally look for are articles, images, club news, trip reports, observations, etc. Please contact Dave and he can review those items. Please remember that the newsletter is always available online on the website. Everyone's mailed a copy by default, but if you would like to opt out of receiving a mailed copy of the newsletter, please let Charlie know. Friendly reminder, as this was already talked about, A, keep weeds clear, but B, if you're hanging out there, make sure the site is locked down, windows are closed, etc. The next general meeting will be September 13th, and I'm going to turn it over to John Garrett for the What's Up presentation. Thank you.
John, you need to unmute. You're mute, John.
Sorry. Okay. It's good I was muted because I don't think what I said made much sense while I was trying to figure that out. The program said I was going to be here in person, and I apologize. I couldn't be in person. I injured my back this week and found out that I couldn't really ride in a car comfortably yet. And so that really was the second reason. The first reason I'm not there is that I tried to make it there tonight, had my daughter driving me. She made a peanut butter sandwich for the road. We got a quarter of a mile away and I started to hurt a little bit. And then she said, I forgot my peanut butter sandwich. So I thought, how perfect, we'll go back and drop me off and send her along. So really it's about a peanut butter sandwich. That was the real deciding moment. But anyway, August is my favorite month. Look at the sky. So I'm going to show you some of my favorites. Let me, oops. There. Okay. Oh, before I do that, most of the pictures you'll see are pictures that I've taken. So I've tried to put out up front what I'm taking my pictures with. Most of the pictures of celestial objects are with my 3-inch telescope. It gives me a wide field of view, and it's very forgiving since I don't have a lot of precise tracking. So the 3-inch is my favorite to photograph with. It also gives you a field of view that's comparable to what you might get with a 10 by 50 pair of binoculars. And then other pictures I take with my 8-inch spent Cassegrain, and then the wide field pictures are usually a 24 millimeter or a 14 millimeter cheap lens on a standard single lens reflex camera. And for the few images that I've stacked, I use Deep Sky Stacker. So those are just little specks up front. And here's a picture of what you might see once it gets plenty dark. 9 o'clock or a little bit later, especially if you're near a dark site, you might look to the north and recognize the Big Dipper. And as you recognize the Big Dipper, you'll probably recognize 3 of the stars of the Little Dipper. And then here's the others that show up only when it gets darker, or you sometimes have to be in a darker location. I find in the city, it's hard to see those other stars. And this is a reminder that you're looking almost north. And we have a comet in the sky very close to the constellation of Ursa Major, the Big Bear. And I've just highlighted the stars that give the Big Bear its name. If you take away the handle of the Dipper, it makes a pretty convincing bear. And this direction here is about where Comet Olbers is. I haven't had a chance to see it this week because of my back injury, but I'm told it's still there. And it's about that location. And it's also moving into the star cluster Coma Berenices. So that should make a nice view over the next week as the comet moves through that cluster. And just a reminder, the ground is a little lower than what it is in this particular photo, since I've taken this one at another time of year, a couple years ago. But that's about as the comet moves through the cluster, the sky, it's also getting lower and lower in the west, just because of the tilt of the Earth as the days go on. So you better look soon, because it's getting lower. By the end of the month, it might be lost in the brightness of the western sky. Then about a month ago, I did get a picture of Comet Olbers. And so here it is in the middle of the crosshairs. And you can see I'm also fighting a lot of the lingering western daylight to get this picture. And also in the picture, if you're going to take a picture in the west while there's like twilight or a little darker, you're going to pick up a lot of satellites. And so this is how many I counted in just a 5-second exposure trying to get this comet. So watch out for those satellites. The planets. We have Venus joining us in the evening sky, and this is an illustration, not a photo of Venus. But you can't miss Venus. It's going to get a little higher and higher over the next few months, so there's plenty of time to see Venus. And Saturn is now kind of coming into opposition soon. And on September 8th, it'll be as close to Earth as we get. It's also going through a time where our view of it is showing the rings in a more and more edge-on view. So the top image sketch of Saturn shows how we often see it through many years. This year, we're seeing it close to edge-on. And I've read that in March 25, we might actually have the moment where Saturn's rings are exactly edge-on to where you can barely see them. And if you miss that, I think there's another one later in the year where it will be like that. And then Saturn over the years will start to open up again, and it will be another, 6 and then about 12 years, I think, until it's back to this little configuration again that we see now. So anyway, imagine the horizon is like this in my picture. It doesn't look right when I rotate my pictures to get a more accurate view of the eastern sky. So imagine the horizon is there when Saturn rises, and there'll be Capricornus over here, and then the constellation Aquarius next to it, and Pisces Austrinus will rise a little later, and Saturn should be right up there in the corner where I've drawn it. And Saturn again will look about like that. And while you're looking at Saturn, it would be worthwhile to look at a couple other objects in that area. One is the Saturn Nebula. So if you got Saturn in one part of the picture, you might as well look at the Saturn Nebula, which is a planetary nebula, which simplest explanation of these are they're dying stars that have blown out their outer layers and sometimes have created sculpted shapes like what looks like its own rings, but those are like protrusions from the nebula. And so it gives the illusion of a planet like Saturn. And then the other fairly bright nebula, common for people's photography interests, is the Helix Nebula. So I've read that you can see that with possibly with a wide field scope. I haven't looked at it, I haven't seen it, but it's one of the targets I want to see how easy it is to pick up in a pair of binoculars or a wide field scope. And then I took Saturn where it was last year and where it was now, and I plotted about where Neptune should be. So in that picture, that's about where you'll find the planet Neptune this time of year. And also in this region is the radius of the Southern Delta Aquariid meteor shower. The peak of the shower has already passed, but it lingers for a couple more weeks. And so you may see meteors emanating from this general direction. And if you want to see the other planets, the other bright planets, you need to look in the morning sky. So last week I got up around 4:30 or so and walked down to the nearest overly lit park and got some pictures of the bright planets in the morning. And I included the horizon in all of its glare so you can get an idea about how high these objects are up in the sky at this time. And here's the constellations Orion and Taurus. And if I move that toward the middle, notice Taurus's eye. There's a star right where Taurus's eye is. That's Aldebaran, often thought of as the eye of Taurus. And it may look that like Taurus has a second eye right now, and that would be the planet Mars, a reddish color similar to the reddish of Aldebaran. And then at the top of Taurus's head would be this bright object, which we know as Jupiter. And then the planet Uranus actually shows up in this very short exposure I took. And also that shows about where you can find it. A little harder to see, but most telescopes, you can see it well enough to see it as a disk. And I have to admit, a lot of people, when the first time they see Saturn or Jupiter, they're just sold for life. The one object that got me most hooked on astronomy was when I saw the planet Uranus for the first time, because I realized, unlike the other bright planets, most of the people who've ever lived have never actually seen the planet. And so when I first saw that through the telescope, it could detect that it was actually a disk shape and not a pinpoint star. That's what got me hooked on astronomy. We have some meteor showers. I'd mentioned one, but there is another major meteor shower this month, the Perseids. And I always hear optimistic reports that under the best conditions, you could see perhaps 60 to 100 per hour. I've never seen that, but I've never been disappointed with how many I've ever seen. And with most meteor showers, this one's better seen in the morning. And that has the double advantage of, in the morning hours, the moon will have set out of the way, so the sky can be darker. But always, if you can get to a dark location, that really is the place to be. Warning, last year, Joshua Tree National Park just got swarmed on the Perseid meteor shower. So these things are getting popular, which is part of the goal of us amateur astronomers and all of our outreach. We're almost too successful in some regard, but it actually gets very difficult to visit dark places. So I wish you luck if you can do that. And then the Southern Delta Aquariids, their peak was just a little over almost 2 weeks ago. Their potential is about 20 per hour, but they should be lingering throughout to the 21st. And here's a Perseid I captured a few years ago when I was just doing my yearly check on whether I can still detect the Milky Way from my front yard as a light pollution project. And I caught a Perseid, very identifiable by its little green in the trail. And this is seen in the constellation Scorpius. So I don't believe that the radiant had risen yet in the east when I got this picture. And also from my backyard, so you don't always have to go out to the darkest locations. I took a camera a few years ago and trained it on one area of the sky where you can see the Andromeda galaxy lower in the center. So I just chose that area to photograph meteors for, I don't know how long, but at least an hour, figuring that if nothing else, I'll at least have a photo of the Andromeda galaxy. And so this is a composite of the 5 meteors I caught. And so I caught enough to plausibly indicate where where those appear to be coming from. And that's where the path of this shower intersects with the orbit of the Earth. And it's kind of like if you ever done this driven in a car in a snowstorm, you have this, it's like all the snow comes at you and then spreads out to the side as you drive through it. It's sort of that kind of illusion. And there's the approximate radius of the Perseids meteor shower. And here's some other landmarks, or I should say sky marks, as to get your bearings in the night. You might recognize Cassiopeia, Andromeda, and the Great Square Pegasus. And this is probably the best Perseid meteor I ever captured. And I didn't capture the whole thing, but I did get a piece of it on the edge of my image. And it really does highlight the beautiful color of these. So if you're ever going to photograph any meteor shower, the Perseids are a great one for their nice green color. You can probably guess why I found this particular news article so interesting. Commonly, I'm seeing a lot of satellites showing up in people's meteor photos. And I've got a lot of pictures of satellites that I once thought was meteors, and I'm not criticizing anybody who makes that mistakes unless they're professional media. If they're professional media, well, that's their job. They should be able to tell satellites from meteors. But yeah, here's something described as a southern Aquariid meteor streaking across the night sky. And the only part they got right in that picture is the night sky. So this is my precedes my warning about advice to how to detect meteors from satellites that will show up in your picture. This picture I took of a globular cluster completely revolutionized my awareness of the problem, in that a lot of pictures I have, because the object brightened and then dimmed, I assumed, oh, that must be a meteor. No, it appears that satellites do that. And so when I've got this satellite that obviously brightened and dimmed and brightened again and dimmed, that made me think, oh, I better go look at a lot of my meteor photos. So that's one of the first things I just because it brightens and dims, I don't assume it's a meteor. Here's one that I thought was a meteor, and I downgraded it to satellite. So the trick I used to verify this one is I overexposed the picture, and then you can start to see how this meteor, quote meteor, continued off to the right and probably kept going that way until it went all the way around the planet. And so I'm referring to that little area there. So if you can extend your meteor by using the exposure, you probably have a satellite and not a meteor. Also, it's good to take multiple pictures of the same area, because if your object appears in more than one photo, especially sequential photos, most likely it's a satellite and not an instantaneous streak of a meteor. And then here's one that's interesting. I've got 3 groups of objects. And are any of them meteors? This one, I would say no. What I found interesting about this is that a slow-moving object, a satellite, therefore, is going to pick up much of the same imaging error as my stationary objects, the stars. So my stars are a little blurry and they've got some motion blur to them. And so does my meteor trail, telling me that's probably not a meteor. It was a slow-moving satellite. And these, of course, if you've got a couple things moving like that together, there's several satellites that are traveling in pairs. So it's got to be one of those. And also you see the image error of these slow-moving objects. This one, I don't know. I still think it's a satellite, but it could be a meteor. It's, you get that gray area. But when you compare it to something like the Perseids, there's no comparison, because the colors really do give away that you've got a meteor instead of a satellite. Now, not all meteors are colorful, but if you do take multiple photos, you may find additional proof that it was a meteor, such as this debris trail from this Lyriad meteor that I captured several years ago. And then there's nothing better than visual sighting of the meteor. You can't, you see it, it's a meteor, it happened fast, that's one of the best ways to verify it. And so this one I actually saw when I was doing my yearly photograph of the Milky Way, to do my light pollution test. And it gave me an opportunity to take my 2 data points of meteors that are traveling in the opposite direction they're all traveling in the opposite direction, but usually we look toward the east because that's where we're going to see most of the meteors. We rarely waste our time turning our cameras in the other direction and looking to see where they go. And so I always assume that if you've got meteors radiating when you look at them, if you look away, you should see them converging. on the opposite horizon, but I've never really wasted my time to try to test that. But these two visual observations gave me a chance to do a partial test. I only have 2 data points, but these two were photographed during the lead-in period, and they almost converge at where I think the anti-point, the opposite of the radiant should be, but I need more data points on that. But it gives me a chance to, that's something you might want to try. If you ever feel like feeling contrary at a meteor shower, turn your camera in the other direction. I'd be very curious to see what you capture. And of course, you can always detect meteors by seeing how they, listening to how they enhance an FM radio signal that is just out of your range. And so I'm told if you, get a station with these frequencies, those frequencies will be deflected by the debris trail of a meteor, and you might hear that radio station do a little louder sound for a brief moment. Okay, on to some deep sky objects. There's so much to look at. All I decided to do was focus on just the Sagittarius-Scorpius area, because that's the area that's going to disappear first as the summer progresses. And so here's a picture I've taken, I think, out in Anza Borrego of the Sagittarius and Scorpius. And here's a portrayal of those constellations. And Sagittarius is actually always surprises me how big of an area that constellation is in. And it even has a smaller constellation inside it a little bit, Corona Australis. Anyway, all of these are I think these are most of the bright Messier objects in this area. So the Charles Messier, his catalog of not comet objects that also happen to be the easiest to find, brightest objects. And so they're all wonderful targets to look at. Almost all of them you could probably find in binoculars in a really dark location. And oh yeah, here's a few, some of the favorites. M6 on a good night, you can almost see that with the naked eye. Here, these nebula are just beautiful things to look at. You don't get this color when you look at them visually, but it's very easy to pick up color in a very short exposed photograph. So you've got M8, M20, and M21. M20 is often known as the Trifid Nebula. And then, so back here, I didn't want to show all of these Messier objects up close, but those are things for you to look for. And what I am going to show, how many of these are globular clusters. And I've been reading some research papers lately that are making a strong argument that these globular clusters are best explained by being remnants of galaxies that got eaten by ours. I don't think the papers were absolute about that, but they're hinting at that possibility. So here's a very good one to see in Scorpius, M4 globular cluster, and that's one over by, you can see it over there on the right. You can see it's very close to the star Antares. And there's another globular cluster in that, NGC 6144. And then M22, one of the brightest, very, very nice to see. And there's also some other interesting objects very close to this that I'll share. And so these are just the globular clusters that are in the Messier catalog in just this area of sky, which happens to be pointed toward the center of the Milky Way galaxy. And if you then add the NGC catalog, suddenly the globular clusters, there are just so many of them to look at. And they all tend to look similar, but they also make some nice combinations of objects within the same field of view. So here there's 2 here in the spout of Sagittarius that are certainly within a binocular field of view. And then here are, there they are. These 2 are very close together. So if you have a telescope that you can actually see the moon in, you can get the field of view equal to the moon. This picture of the moon is of the same relative size as this area of sky. And so you might be able to see the 2 together. And then this particular one I found by accident because I typed in the wrong number, and it took me to a nebula that I could barely detect in the center, but it also is my picture of NGC 6544. But this is an area that if you're an astrophotographer, I'd love to see what you come up with. It's something I want to get back to and actually bring out the nebula that's in the middle. And all this is very close to the M8 star cluster. And here's M8, and then here's a couple globular clusters next to it. Again, very beautiful, beautiful color to the globular clusters too. And then, let's see, I think I covered some of those, but certainly not all of them. Now, if I switch to another favorite object of mine, planetary nebula, this whole area is swarming with planetary nebula. The PK catalog are very faint objects, so I take them out. I haven't yet got one to show up on my camera, but a lot of these others show up beautifully in just a very short exposure image with, you don't even need to do a lot of stacking, if any, to bring them out. So here's a 6153 in Scorpius. That's it right there. Here is the Bug Nebula in the tail of Scorpius. And then here's 6563, a beautiful little green splotch. And this is in my small refractor. And if I bring it up in my larger scope, I can get a little better image. This one I stacked. And then what I love best about these things is they show up these green little stabs of light in the dark. And another one here, an Ophiuchus. And then a couple, this one's kind of neat. You've got a planetary nebula and a globular cluster in the same area of sky that you'd have a moon. So it's in about a half degree. And then another one here, we've got 6445 and the globular 6440. And I think this one was with my bigger scope. So yeah, and then another one, little green stab in the dark. And another little green stab in the dark. And here's one where right near M22, there's a globular cluster and one of those green stabs in the dark. And that's the close-up of that one. And then in the other direction from M22, there's another planetary nebula, that little green splotch, and another globular cluster. So there's just some beautiful compositions of objects in that area that don't take a high magnification. In fact, high magnification works against you. And if you have lower magnification, you can get by with lazier tracking. I don't guide my telescope. I've just never developed the ability. I've never bought the equipment. So I enjoy seeing what I can get with a 30-second to a 3-minute unguided exposure. So anyway, next thing I want to show is there's a special star we're expecting as a possible nova this year. And so this picture was taken in June of the Milky Way. Imagine the Milky Way. This is a really wide field image taken with like a 6mm lens. And imagine the Milky Way is directly above us right now. And if you then look over to the east, you will see this group of stars called Corona Borealis, the constellation Corona Borealis. And at that same location, I took this picture, and those pine trees are like 100 feet high at least. And so this picture is actually pointing up in the sky this time of year at about a 45-degree angle. So the constellations are really still pretty high up. So this is Hercules. A lot of people see this as a big butterfly, but it's also Hercules, the strong man. And M13, the globular cluster, is a very famous Hercules cluster worth looking at while you're there. But the object that we're interested in is in Corona Borealis. And if you take the alpha star, the brightest star, and use the two stars next to it that almost form a line, and imagine that line becoming a curve, that'll take you right to where T Corona Borealis is. And that is the star that's expected to erupt anytime, possibly this month, and present itself as a recurring nova. So it's very close to Eta with that little E symbol, the star Eta Corona Borealis. And so here's an image with my smaller scope with Eta Corona Borealis. And then I've got marked T Corona Borealis. And it doesn't look like much of a star. It's a very faint star, but that's it. And what's going on at that star? Oh, yeah. And I'll come to that in a moment. Here's an example of how it might look. This is a nova in Sagittarius, maybe about 10 years ago. So if you look and recognize the teapot shape of Sagittarius, you might see that there's a star that doesn't usually go there, and it's this one. So that was a nova in Sagittarius, and you can see here's Sagittarius without it, and here's Sagittarius with that nova. So we might get as a display something like that. And what's going on is you've got a gas giant and a white dwarf, and it loses mass to that white dwarf so that the surface builds up. The pressure allows nuclear fusion to start. And then when it reaches a critical point, now cover your eyes when I do this, and you've been warned, it goes from that to this. And that's what we see for a couple of weeks until it fades. And so here's Corona Borealis, and my best estimate as to what it will look like is there. And so you see that little star that I've drawn. And so you might see that. So you get this rare moment every 60 or so years. I forget the exact number. That star joins the constellation, and we're looking forward to it. And if you miss it, there is a way. I do have a consolation for you. You might just draw it in and send it into some local media, and who knows, maybe they'll publish it. Anyway, thank you for the giving me the chance to share all these with you.
Thank you very much, John, for yet another great presentation. Okay, so our speaker at this meeting has gotten his undergraduate degree from Caltech and his PhD from University of Hawaii in 1992. He has published more than 70 peer-reviewed research papers and developed a citizen science project for the 2017 total solar eclipse. He left the research field in 2018 and is currently an electro-optical engineer. He holds 2 patents in the field of image processing and continues to publish research papers in the field of astronomy as a hobby. Please join me in welcoming Dr. Matt Penn. Matt.
Hi, thank you for the invitation. It's a pleasure to speak with your group tonight. And let me see if I can share my slides. Okay, how's that? Excellent. It's a pleasure to speak with you again tonight. And what I'd like to do is to tell you the story about how we've developed a citizen science project for the 2024 eclipse last April. The path wound through the 2017 eclipse, and I'm sure that many of you saw both of those events. My current affiliation is I'm working in industry here in Tucson, but I also have an adjunct faculty appointment at Southern Illinois University, Carbondale. And you might know that the paths of the 2017 and 2024 eclipses crossed in Carbondale, right over top of SIU Carbondale. So my colleagues there have done most of the heavy lifting, most of the work for this project. I don't really deserve to be the first author on this paper. Bob Baer and Corrine and Harvey Henson and Chris Mandrell have done a lot of work. David Idavita is a colleague here in Tucson, and I'll discuss some of the projects that he's looking at for a follow-up program. Mike Conley is involved in the project as well. He's been involved since 2017, and I'll show you a couple of images in this presentation that he's taken. And then, of course, the members of the DEB initiative team, all 378 of them have contributed, and without their work, obviously none of this would be possible. We were funded from NASA and from the National Science Foundation for this project. And we also had individuals contributing to the program because this was an international project for 2024, where the path went across Mexico, the United States, and Canada. We could only use federal money to support volunteers in the country, and so we had to develop other sources of funding for the Mexican and Canadian sites. And I'd love to answer questions. If I say anything that piques your interest or confuses you during the talk, please chime in, and hopefully we can make this more of a discussion. So I'll start out with maybe some basic introduction. A big question that people ask, including my scientific colleagues, is what the heck can you do from the ground in terms of science during a total solar eclipse? And so from the ground, you can't see the corona of the sun during the day because the scattered light in the atmosphere of the Earth limits your ability to see the corona. The corona is about 1 million times fainter than the disk of the sun. And just like in this example, hopefully none of your houses are this dusty, but imagine you're in a very dusty room and you held your thumb up to block light that was across the room from you. You'd see bright dust particles because light from the source, from the light bulb, is scattered off of those particles and scattered into your eyeball. Same thing happens with the Earth's atmosphere. Processes are slightly different, of course, but we get scattered light from the disk of the sun that increases the background around the solar disk and blocks our view of the solar corona. Now, a total solar eclipse does two things that are really important. First, it blocks the disk of the sun, which is critical to see the corona, but it also casts a shadow on the atmosphere of the Earth. And so the scattered light that we see around the solar disk and around the moon is reduced by a factor of about 10,000 compared to a normal day. So this allows us to do some very special things during totality, during a total solar eclipse, that we're just not able to during the rest of the time from the ground. Now we can build telescopes called coronagraphs that have internal optics which block the disk of the sun, but they're still limited by the sky brightness, by the scattered light in the atmosphere of the Earth. And so again, a total solar eclipse is a very unique opportunity to take data, even with small telescopes, that can be scientifically very valuable. What I'll talk about through this whole through this evening tonight is all about white light, so continuum observations. So we're not using any filters in our observations. We're just looking at light that's scattered off of well, that's white light, so continuum. The reason that we do this is because the corona is very hot. It's got a mean temperature somewhere around 1,000,000 degrees Kelvin, but it also has a lot of temperature fluctuations. There are parts that are cooler, and by cooler I mean only 10,000 degrees, and some parts that are even hotter, 3 million or 5 million occasionally. So when we're using filters to look at particular emission lines, say, we're limiting our field of view to just those temperatures. So for instance, when you use an H-alpha filter to look for prominences around the limb of the sun, you're looking specifically at about 10,000 Kelvin, a temperature in that range. But when you use white light, the process that produces that white light emission or intensity is when light scatters off of electrons. And electrons represent gas at all temperatures. And so we don't have any temperature confusion when we use white light. We're seeing all of the plasma in the solar corona. So that's what we can do from the ground. But of course, other colleagues of mine at NASA do things from space. And obviously there's no scattered light because there's no atmosphere in space. So a lot of people are wondering, well, what can you do that's different from what NASA can do from orbit? So here I've got a figure that sort of hopefully gives you that idea about what we can do. NASA has several missions that are looking at the corona of the sun. An excellent one that's been around for a while is called the SOHO mission, and an instrument on board there called LASCO C2 looks at white light from the solar corona, but it only goes down to about 2 solar radii. So this inner donut here is where NASA blocks the disk of the sun and prevents scattered light from entering the instrument. NASA also looks at the surface of the sun, the corona projected against the surface, using very bright ultraviolet and extreme ultraviolet emission lines. And in particular, the SDO instrument called AIA does this, but they're using specific filters. So they're looking at very specific temperature regimes in the corona, and they're not getting all of the plasma that a white light instrument would do. So what a total solar eclipse does is that it opens up this window and allows us to take data from this region of this inner solar corona. Now, this is a really old image from 2016, where we took data during an eclipse in Indonesia. And our field of view was meant to fill in this region, and it doesn't quite do that, but it captures a lot of the plasma that's inside this sort of invisible area that NASA instruments cannot measure well. So why do we want to look at this? Well, of course, a lot of interesting physics is happening there. I'm sure that you've seen movies of the solar corona and how the solar wind is expanding from the surface of the sun. And sometimes in the solar wind, you get storms called coronal mass ejections that move even faster. These things can go at 1,000 kilometers per second, the fastest ones. So NASA, of course, is always wondering how these objects, coronal mass ejections, and also how the solar wind is accelerated off of the surface. If we look at Doppler shifts at the surface of the sun, there's no blue shift, there's no expansion that's visible. But out here in the LASCO field of view, we can see these things moving at 200 kilometers a second or up to 800 kilometers per second. Unfortunately, the speeds are constant out here in the NASA LASCO field of view. So somehow the material is going from 0 up to, say, 250 kilometers per second. And that process is hidden behind this region that NASA normally can't observe. So by observing this region during a total eclipse, we get, a unique perspective on how the particles are accelerated. Now, I'm sure everyone was accelerated sometime this week as you hopped onto a freeway in Southern California. And so think about it as maybe a freeway, right? So the solar wind has particles that are moving at more or less a constant speed, say 200 kilometers per second, just a little bit slower than some of the drivers in California. But the acceleration happens on the on-ramps. And so the inner corona you can think of as the on-ramp to the solar corona, where particles accelerate from 0. When you're at the top of an on-ramp, you're not traveling. And then you hit your acceleration pedal and merge with traffic, going at the speed that NASA can observe further out. Now, why is this interesting? Well, you all know, of course, that a Ferrari accelerates differently from a Toyota Camry. I have a Camry, I don't have a Ferrari. But you can tell a lot by how a particle or an object accelerates. You can understand the forces that are involved. For a car, you can understand the engine that's involved, for instance. And so it's critical for us to really gain a physical insight about the solar corona to understand how that acceleration happens. So this is our goal, was our goal for 2017 and also for 2024. Now, during eclipse from any one site, though, an eclipse can only last at most, I think, 8 minutes. In 2017, we were limited to just 2 minutes at one particular site. And even if you're taking images, during that whole 2 minutes, a particle of gas, only moves a small distance in the solar atmosphere in your telescope's field of view, across your camera. And because of that small translation, you get a very poor measurement of the velocity of that gas particle. So for any one site, you really can't do this experiment. But if you strung a bunch of telescopes together, as we did in 2017, the eclipse started in Oregon and then ended in South Carolina. And if you combine the images from all of these different sites, you get 90 minutes of time rather than just 2 minutes. And so during those 90 minutes, you have a lot of motion. You can see particles of gas moving across your camera with enough, and measure their velocity with enough accuracy to make a valuable measurement. And so that's what we did in 17, and that's our main goal for the 2024 scientific data as well. Turns out that there aren't enough solar astronomers to man all of those telescopes across the country. And so what we did instead is to develop a citizen science program where we would have volunteers who were, otherwise innocent people, high school students or museum workers or undergraduates, unsuspecting undergraduates, and we would train them to take astro images during an eclipse. Now, it's one thing to go outside in your backyard, and take an image of the night sky in the comfort of your own, home. But to go to a different place and set up a telescope in a field someplace in Nebraska, and to have a very specific, minute where you have to collect data and nothing can go wrong, is a very different situation. And so we spent a lot of time training our volunteers, and the team that we put together to do this in 2017 was fantastic, and we had a lot of success. So here's just a list of our collaborators from 2017. Each of these groups had an observing site. We provided, or using our NASA funding, and in 17 we had some private donations. We provided an equipment package that they kept, and they still have today. And we trained them during the buildup before the eclipse, and they collected data. They're also all co-authors on our science paper, on our results paper at the end. So, we had some excellent results. In terms of education and outreach, it was a tremendous success. We had local newspapers and TV stations find out who their local volunteer teams were and do stories about them, and some at the national level as well. But we did collect some valuable scientific data. So there are two things. One was that we were really proud and excited to collect new scientific data that no one else had collected before. And then after we collected it, we realized that, hey, no one's collected this type of data before, so no one knows how to analyze it. It's very unique, and the solar corona has its own set of unique problems. So it took 3 years of work to combine data from our 70 sites using what we thought were identical telescopes, but of course they have some variation, and to make scientific measurements. So our paper finally came out in 2020. It's in the publications of the Astronomical Society of the Pacific. It's free access, so you can download it and take a look at it if you like. In detail, I'm showing you an expanded view of our imaging. Here on the sort of southeast limb of the sun, we saw the remnants of a coronal mass ejection that had gone off before the eclipse happened, but we still saw some particles moving outward through the corona during the time of the eclipse. If you can see, maybe you can pick out some arrows that show the direction of motion of the gas particles. This is from 5 images, I think, across an hour of time. And so what we did is we plot then the radial motion, the outward motion, as a function of height. So along the x-axis, we have height from the center of the sun. 1.0 is, of course, the very limb of the sun. We can't see that. But as we move up higher, we eventually get to the height where LASCO can take data and make measurements. And LASCO saw this event moving outward through its field of view at about 250 kilometers per second, again, with a constant speed. So that's this flat line up here. And our measurements are the individual data points with some error bars representing the inaccuracy in our data. So we did it. We measured the acceleration, but of course it's not pretty. I guess that's an understatement. It's very difficult to explain. The simplest explanation would be that this material would be subject to a constant acceleration. It would be moving outward at under some constant acceleration. That would be 15 meters per second squared here, the dashed line. It doesn't follow that at all, not even close. We can dream up some other ad hoc model, the straight line here, not even close. So, like all good research, this opens up more questions. But this is one of only 3 measurements of its type, and the only type of measurement like this using white light data. So our plan for 2024, excuse me, was to make the second measurement using white light data from our team. So we developed, using our contact group, we developed a project for the 2024 eclipse. One sort of failure, because the data was so hard to analyze, was that we didn't have any real-time presence in 2017. And we wanted to do that in 2024. So we had the audacity to name the project the Dynamic Eclipse Broadcast Initiative. Right there in the name, we were going to broadcast it. So that was a priority goal, is to make a broadcast. Of course, we'll collect data just like we did in 17 and look for the dynamics of the inner corona, look for acceleration. And we wanted to have a larger, make it an international program, have sites in Mexico and Canada, as well as the US. Again, we wanted to fund our volunteers so that they could keep their equipment and use it for follow-up projects. And I'll talk about those at the end. So here's a sample image from our 40 millimeter telescope. And I'll talk more about the details of how we produced that. So the improvements that we made, well, we wanted to make the cost lower because writing proposals and getting money is always a challenge. And if we were able to reduce the cost, we could be more successful. So for each site, we reduced the cost almost by a factor of 2, down to 1,800 in 2024. We wanted to standardize our data collection. So I'm sure any of you who do astrophotography know about SharpCap. And so we used SharpCap to collect our images. And in particular, we used the scripting part of SharpCap with some Python scripts. And we had a larger field of view. So I'm giving you a preview of some of our results. Here's our field of view in 2024 compared to 2017. So we get the overlap now completely with the LASCO NASA field of view. During the buildup, we did a couple of tests. I shouldn't spend too much time on this, but we thought maybe we were going to use Raspberry Pis initially. That would be very low cost. And so Fred Isbiner and his colleague took a cruise to see the Antarctic eclipse in 2021. And they brought a Raspberry Pi, which was packed, very compactly in a Tupperware container. Unfortunately, although they did see the eclipse, they're the only cruise ship that was able to see it. The boat had to turn 180 degrees right before the eclipse, and so they didn't have time to run across the boat and set up their equipment. They only got an image of the partial eclipse through the instrument. And here's the ocean, and here's the cloud deck. So you can see the captain of the ship did a fantastic job of just getting it in the tiny window that they had available. If you know about Raspberry Pis, you know that they developed a shortage after that. And so we gave up on having Raspberry Pis in our project, but instead went with a more standard setup. So it's tiny. We have a 40 millimeter ASCAR. This is the FMA 180 Pro, so 180 millimeter focal length. It's a 5-element optical system. It's fantastic. It's a great little telescope. We used a Player One Neptune M camera. It's a 3K by 2K monochrome camera. And then we use the Ioptron Skyhunter mount. It's a go-to mount, very compact and relatively cheap. So that combined with the laptop, this is my micro laptop. So we had larger laptops for the project, but the whole system combined with the laptop was about $1,800, and it could fit in a backpack. We did some sort of fancy practicing. The most important part of this slide is that we needed to do high dynamic range imaging. So to capture the inner corona and the outer corona across our field of view, the intensity drops off by a factor of about 3,000. And you can't do that very well on one exposure. So we took sequences of different exposures, in this case, 4 images from 0.4 milliseconds up to 400 milliseconds. We practiced that on the moon, and here's a total solar eclipse, total lunar eclipse in October of 22. And then we recombine those images and properly normalize them to make a final HDR image. And here you can see the eclipse moon and the surface with the faint stars in the background. We did some fancy stuff where we subtracted out the image of the lunar surface and then just looked at the resulting shadow image and projected it against the stars in our field of view. And this is the kind of image that we were able to create from that lunar eclipse. So during the practice leading up to the total eclipse, we were doing some fun things. To get images during the partial phase, 40 millimeters combined with maybe some difficulty focusing and poor seeing during a hot day makes your images a little iffy. So what we found was a package called Planetary System Stacker. It could be called from a Python command line or from a command line if we had the Python version. And so within SharpCap, we had a script that collected images for 15 seconds of time at about 15 frames a second, so about 200 frames. Then we would call Planetary System Stacker to stack the 80 best images and then do a wavelet filtering on the image as well. So you can see some details of very small sunspots and some plage, some bright areas at the limb of the sun. And these images then, during the partial phase of the eclipse, were uploaded to a website every minute from all of our sites. 1 year before the eclipse, the team had a chance to practice. There was an eclipse in Australia, very northwestern Australia. And so team from Carbondale went to this eclipse. They got some nice deep sky images at night, very dark. The coast of Australia there is very dark. And some full frame images during the partial phases. But this is a very valuable trip because during totality, bad things happened, and we didn't capture any images of totality with our DEB equipment in Australia. But we learned a lot. So, thank goodness we practiced during the pressure of a total solar eclipse. There's a backup telescope with the group, and this is an HDR image produced from the data from that backup telescope. So the corona is quite impressive. And if we had captured some images, they would be lovely, but I can't show you any because we didn't get any. But we learned some images and learned some valuable lessons and made some changes. Coming back from Australia, the team, especially in Carbondale, dealt with all the equipment. So we had 80 80 mounts and computers and telescopes shipped to Carbondale, and they were shipped out to our teams across the country. Then we ran practice sessions during the day. Here you can see some sites from Kentucky through Tehachapi, Oroville, and then a couple of us in Tucson taking data of the sun at the same time. And we did this, as often as we could, as often as volunteers were able to collect data to practice with. And so, this is kind of a unique citizen science project. If you look at a lot of the citizen science projects, you're analyzing data that people have already collected. But here we're asking people to collect the actual data. So there's a lot of training that went into this. And following what we did in 2017, we had sort of a hierarchy where we had a core team and some regional coordinators. And so a regional coordinator like myself would pull out 6 or 7 teams from across the country and work with them during training and practice sessions and answer their questions and try to get them up to speed, give them the support that they needed. So in the end, we had 82 teams. The teams ranged from just a single person in one case up to 30. I think Chula Vista High School, just near San Diego, had 30 students involved in their team. And like I said, we did imaging outside of the path of totality as well as in the path. The National Science Foundation money was targeted in particular to work with a film group doing a film called Einstein's Incredible Universe. I think it's still in production. And they targeted young women in particular. So we had 20 teams of young women who, again, got their equipment and training. Their training was maybe a little bit more intense and more focused. And so they had a slightly higher success rate than the rest of our group in general. But look for this movie. I'm not sure exactly what the timeline is, but hopefully it'll be coming out. It'll describe their experience as well as experiences from the 2017 project. Actually, the great thing was that some of my students from 2017 were then mentors for these groups in 2024. So, the outreach here is a big component. And so Carbondale is doing some really interesting things. They had a big event in their stadium on campus where NASA TV did a live webcast. They're following up with some other star parties. I'll show you one in particular, October 14th. This will be a virtual star party that everyone is invited to join in on. And then, to summarize it, we have a map of our sites. The out of eclipse sites, the out of totality sites range from a site in Puerto Rico to a site in Vancouver. And then along the path, we had 68 sites. The ones marked in red had real-time upload capabilities. So they would have a video, basically a video signal that was uploaded to NASA TV. And some great images came from Mazatlan from the first group when the eclipse first touched land. And then some of our sites outside of path of totality are listed here as well. But then during the path, and you can still look at this website today, we had a website where images were uploaded. So in this case, you can see that some of the sites did not provide data. They were clouded out. During the partial phase, a site would upload 1 image per minute, so you can see the progression of the partial eclipse. And then during totality, we would go dark and focus on collecting the data, but after totality, we would send 1 processed HDR image to the site. And so we provided more or less real-time images of the solar corona on this site. So on the day of the eclipse, I happen to be in Texas with my wife, and this is all we got. A little 10-second hole opened up during totality, so we saw something, but got nothing useful from the data. So we had a slightly more than 50% success rate, and I'll show you some more statistics in a bit. But the internet impact was, I'm still astounded by this. So this is not quite web hits, this is media impressions, which is a combination of web hits plus broadcast media and some other things folded in. But as a baseline, the SIU Carbondale media impressions, a year in advance were, for this 10-week period, 672 million, and for this 1 week around the eclipse time, or a year before, were 23 million. But in 2024, it's 14 billion. It's just astounding to me how many people were involved and active on the web pages and with the media. And around the eclipse, it was 1.7 billion. Just huge numbers. The internet is an unstoppable machine. So we made an impact there that we're very proud of, and hopefully we can do some continuation of that during our follow-up projects. In terms of the sites, here we are in Texas, and so as you guess, the sites that are light gray are all clouded out. Everybody there was hoping for the best weather. The forecasts were the best, and the day of was the worst. We had some good luck in Mexico, and of course in the Northeast in Maine, we had some excellent data, and some spots along the path in between were good as well. So basically 30 of our sites out of 68 in the path, got no data, but slightly more than half, 38, did get data, and we're currently looking at that. And then the sites outside, if we look in totality, again, slightly more than half of our sites collected data during the day. And so here's what the raw data looks like. And the partial, like I said, the partial images were processed on location. So although we collected 3 terabytes of data, a lot of that was processed at the laptop. So we didn't have to upload all of that, but instead we've uploaded about half a terabyte, 500 gigabytes. Here are our 4 exposures. This is just a sample partial phase, but 0.4, 4, 40, and 400 millisecond exposures from one particular site. The good news is that we can see some stars in the longer exposure images, and we've been using these stars to do the image alignment. We had no stars in 2017, and the image alignment is very difficult without stars. And so we're developing our process now using these sites that do have stars, and we'll apply it to the other sites at a later time. But as an outline, each site, we have about 40 sets of these HDR subframe groups. We've done the dark and flat correction, and we're currently aligning the frames that do have stars in the background. The goal soon is to produce an HDR image averaged over all 40 for every site, and then to combine all of the sites that collected data into one continuous sequence. There are a lot of steps that I'll skip over. One of the main things, though, is that I said there's about a factor of 3,000 intensity gradient from near the sun to the edge of the field of view, and we want to remove that so that we can see the corona. So removing the radial intensity gradient is where we're at now. And what we found is that the CMOS camera is slightly nonlinear. And so where the exposures butt up against each other, you're trying to match the highest signal level of one frame with the lowest signal level of the next frame. And so you can see these rings, these concentric rings. These are limiting our ability to, or will limit our ability to align the images. So we're looking at measuring the nonlinearity and correcting for it at this point. But these are some really early attempts to remove the radial gradient from this one site to show you, or 2 sites, to show you the kind of structure that we're seeing. Rotation is also a problem, and even though these are supposed to be identical telescopes, they vary in image scale by something like, well, what we found in 17 was 0.5% up to 0.8%, almost 1% in image scale. And we have to correct for that. Otherwise, we can't align the images well. So we're looking at rotation by looking at the pre-eclipse data and aligning our sunspots. So here are 2 sites. I forget exactly where they are, but at the same time, you can see the moon is at different locations. Because the Earth is round. The pre-eclipse observations are going to be useful for establishing the rotational offsets between or among all of our sites. And I think this summarizes what we're doing in our next step. So what's next? And I'm trying to go through this a little quickly. Well, there happen to be a couple of more eclipses coming up. So in 2027, there's a wonderful eclipse going across northern Africa that, in theory, allows 2 hours of coverage from the start here in either Portugal or Morocco to the end in Somalia. But I don't think anyone is going to want to go to Somalia to collect data. But this is a fantastic opportunity again, because it allows a very long baseline and will allow us to make more precise velocity measurements in our data. And then in 2028, we have an eclipse going across Australia. So we're hoping that with these lightweight and inexpensive and portable telescopes that we'll be able to field groups of people to make a few measurements for these eclipses, and maybe even support local groups in Egypt and Tunisia and Algeria to purchase them. But one of the main projects that we're working on now is a white light solar flare project. So the idea is that, and I'll talk about the science in just a second, but we want to take images at 30 frames per second, so really rapid cadence, and look for flares in white light in continuum. Now, they have a very weak signal unless we're talking about very strong flares. So X-class flares and higher are things that we think we can detect. We have a training procedure written now, and we're looking for people to join in on this project. The longer sort of baseline we can get, like from Maine to California, allows us more hours of sunlight, and we can capture more flares that way. And maybe this is more detail than you want, but we have made observations of flares in white light, although this is in infrared, where the flares are brighter. And it turns out from the ground, we can capture much higher cadence data than they can from space. So the structures that we see in the flare intensity profile from the ground allow us to test different types of transport mechanisms for the electron beams that are involved in the particle acceleration in flares. So we just came out with a paper about this in monthly notices. Collecting data, this is collected at 1 frame per second. And if we can collect data at 30 frames per second, it'll be unheard of in terms of white light flare data. Another follow-up project, though, at night involves circumpolar variable stars. David Idavita here is looking at AE Ursa Major, and it's a very short period variable, so you're able to capture a whole cycle of the oscillation. I think there are some interesting variations on the sort of standard light curve, and I think David is excited about being able to produce a lot of data to look for those small variations. And as was mentioned before by John, T Corona Borealis is about to go nova, and David and Mike Connolly are monitoring that. It's just a start, though. I mean, it's a nice telescope. In 17, we actually took some exoplanet observations, and Rob Zellum, who's actually giving an AAVSO talk tomorrow, published some of those in his paper. We can look for solar oscillations, and Jeff Weiss measured some asteroid light curves as well with our equipment. So it's really the tip of the iceberg. Astrophotography with the system is fun. Here's a M101 and the supernova, extragalactic supernova that was there. And with upgrades, here's my favorite shot of the Rho Ophiuchi complex from my backyard with a better camera on the telescope. So anyway, how could you get involved? Well, if you're excited and want to join our solar flare observers group, please let me know. We have some beta sort of instructions now. We can join nighttime projects or propose your own. If you're interested in the eclipses coming up in the next few years and are willing to travel and carry a telescope with you and take some data, please let us know. And then finally, like I said, in October, we have sort of an online star party from Carbondale, and we'd welcome your participation in that. Okay, I think I've gone over time. I'll stop there.
Thank you, Matt, very much. What a great presentation. What a great project that you're doing. Wonderful. Thanks very much for accepting our invitation and presenting us this. So now the floor is open for the questions. people online can, as usual, use the Q&A section to sending their questions. And let's start with people in person. Barbara, do we have any questions?
Any questions? Yes. The question was, what is the contact information to get involved?
Oh, I left that off. Right now you could just email me directly. My email is mattpenn, lowercase, 2015 at gmail.com. And I could send a follow-up email to people. People in your club have that too.
Is that something, Raisa, that we can maybe put on the information online for the talk?
Yes, I'll arrange for that.
Okay, great. Yeah, any other questions at this point? Yes, sir. As part of the project, you mean? The question was one of the members here has his own telescope, and wanted to know if with the appropriate auxiliary equipment that you were talking about, is that something that could be used for one of the upcoming eclipses to participate?
So for an eclipse, we've tried not to do that so far. And I shouldn't exclude that from the next eclipses. The idea of having identical telescopes was that we would minimize the amount of data analysis that we would have to do, and even with identical telescopes, it was very difficult. So with telescopes with different focal lengths and different characteristics, it'll be even more difficult. Hopefully somebody younger than me will be smart enough this time to solve that problem before 2027 and 2028. So I won't rule it out. But certainly the camera and the collection computer and the software would need to be identical. We would need the same cadence and the same exposures.
Mm-hmm. The question was, do you have telescopes that would be sent as part of the package for those that participate?
We hope so. Every year it's a challenge to get funding from NASA, particularly since I'm an amateur astronomer now. But who knows? The Citizen Science program has been very supportive of our work, and we again hope to be able to support people with equipment packages for our future projects. So stay tuned.
That might,
is
for
all I
people
can
that
say.
might be willing to pay for the equipment themselves. Would you have the information available that would allow them to put together the correct package?
Oh yes. Gladly send you a spreadsheet with links to all of the vendors, and yeah, we'd be happy to help with that. Yep.
Great. Other questions? I think people are thinking about it. Are there any online questions yet, Raisa?
Yes. So, John, did you have your hand up? Do you have a question?
Actually, Emma thought I was going to get the question in before she did, but it was her question about contact information. She texted me. I was going to ask it, but she got it answered. Thank you.
Okay, great. Thank you. So this question is about your recruiting process. Can you explain more? How did you recruit your volunteers, and how did that work?
Oh, it was interesting. In 2017, we had coordinators in every state, and they were the people who basically did the recruiting. For 2024, it was a more general open call, and I don't think we turned down anybody. So I think we may have started with only half of the people that we needed, and kept opening the call and trying to have things in Sky and Telescope and advertise the project. So eventually we had a lot of people involved. The training, I mean, it depends. I'm sure a lot of you guys are very experienced astro imagers, and so you'd find this pretty easy to go through the training. But when we had high school teams that wanted to get involved, they would need to have a couple of months of training at least. So we had a cutoff, I think it was in late January this year for our groups, and we had to have them all identified by then.
Okay, so you didn't need to do any like a vetting process.
So in retrospect, yes, there were two groups that we should have vetted that got equipment and disappeared. So I would have to say that I'm impressed overall with the integrity of most people in our field. But in terms of vetting, we may do that in the future. But the other hand, the other important thing is that we didn't pay for any travel. And so when we're talking about eclipses now in Africa and Australia, there's a big expense that people will have to, assume personally.
Okay, and there is another question from a person who's part Moroccan, and she's referring to 2027 eclipse, asking if you've been in touch with the astronomers of Okaimeden, if I'm not missing that up, as observatory in the Atlas Mountains. Apparently, they are very good at public outreach.
No, and I would like to get in touch with them. So if there's a way that you could forward that information to me, that would be fantastic.
Sure. So yeah, if the person can send in their contact info, I'll forward that to you, Matt.
Thank you.
Great. Barbara, you have questions in person?
The question was for the North Africa eclipse, is that going across Egypt?
Yes. So the path starts in Portugal and in Morocco, skirts the coast, goes through Egypt, a little bit in Saudi, and then out through Somalia.
He wants to know what date would it be in Egypt in Cairo?
Yeah, so the eclipse is on, it's August 2nd in 2027.
Okay, so you're going to
And-
travel there. I think he's putting it down on his calendar.
Excellent.
We had a correction from someone else in our audience saying it wasn't actually going to cross Cairo.
Oh, okay. It may be south of Cairo then.
So
It's hard to see from this map.
he says it's 500 miles south of Cairo.
Yeah. Okay.
This particular audience member is Egyptian and is familiar with Egypt. Any other questions? And not at the moment.
Okay, sure.
Do you have?
I do have more questions online. So this question is for coronal velocity observation, how do you resolve the direction of travel? It can be coming somewhat towards or away, or traveling at 90 degrees from the observer.
Yes, exactly. And so that's an ambiguity in both our data set and in the LASCO data set. It wouldn't be unlikely to be traveling directly towards us because we know that the flow is mostly radial, but it could be at some angle from the limb. So what we're projecting there is line of sight velocity, and the angle is, there's a cosine theta ambiguity in there.
Okay, great. And you mentioned that what kind of software you use, the CAP software and then the Python script. So how much of the software side was automated? Did you need to just only train them on the handwork, or where they need to be trained on software as well?
Yeah, the software was fantastic. SharpCap is an excellent product. I'm not, although we got a lowered a cut rate deal, I'm not really sponsored by them. But the idea was that from the start of, or just before the start of the partial eclipse, up until about 5 minutes before totality, they pushed a button and then they just looked to make sure that the mount was tracking properly. They kept the image centered. So the software would crank out these images every 60 seconds. It would automatically upload the image to the Carbondale webpage. Chris Mandrell did a fantastic job writing that code. And then during totality, they stopped the partial program and ran the totality script. And most of the teams were able to push the button and then enjoy totality, watching totality without paying attention to the computer. And then there were some calibration steps, but Chris did a great job with the software. And yeah, it was as soon as all the bugs were worked out after Australia, it was running very well.
And you mentioned only some of the observers had the thing to do the live broadcast. So was that because they were not able, the others were not able to secure an internet connection, or was that selected somehow?
That was selected by NASA TV. So they sent particular boxes. They're called ATEM boxes to sites where they wanted live broadcasts, where they were hoping the weather would be good. And so actually I tried to use one in October during the annular eclipse and it failed. So there were some hardware issues with the NASA equipment, but NASA TV was the one who selected those people.
Okay. Barbara?
Any other questions? No, everybody is being very attentive, but I don't see any hands raised.
Okay, and so while that's the case, so Matt, you mentioned that you collected terabytes of data. How much of it did you trash versus how much of it you were able to extract information out of?
Yeah, I think that that 950 gigabyte number represents the images that look like they might be salvageable. So I'm sorry, was it 950 or was it a half? It's late for me, sorry. It was 500 gigabytes. We think have data that is salvageable. So the 2 or 3 terabytes of data, 2.8 terabytes, included all the partial phase, and we're using that just for rotational alignment. We're not really doing science yet with that. So I think, we could have collected about a terabyte of data if things were perfect, and we've got half of that from the project.
Okay, and you also mentioned that your goal was to let the people keep the equipment, right? And you're doing follow-up project with them. Is everybody participating in the other projects?
As you can imagine, there's a little bit of burnout. So we haven't had a lot of participation now, and in particular with our academic teams. I know that the local Tucson high school that I work with, all those students have graduated. So as soon as the new flock of students comes in the fall, I'll be pestering them to get them involved. So there's a natural sort of academic ebb now, but we hope to pick it up in the fall again.
Thank you. And do you have statistics on how many man-hour you spent on training all these teams?
I don't, because I'm afraid to look at that, but I'm sure somebody does in the project who's braver than I am. The sort of the branching out sort of the structure that we incorporated was really efficient. We tried to use, let me back up and say that there's a great book about leadership called Multipliers, where you go from sort of a one leader model to a leader that produces many leaders. And that's what we used in 2017. And we followed that idea through 2024. So training people and being able to delegate, that work for them to train other people really pays off a lot in terms of efficiency and also just lifting up everybody involved.
Okay, great, thank you. So let's do another last call for the questions in person, Barbara.
Last call for questions. Yes, sir. I'm sorry. He wants to know whether the project in North Africa would be affected by heat waves, if there's a heat wave at that time.
Oh my, yes, it certainly would. And you can imagine that the 2017 eclipse was in August, and so yeah, the seeing is affected, and so we're really looking for observing locations that had the best possibility for providing good seeing during a heat during the noontime sun. So, the equipment, I rigorously tested the equipment, on my roof in Tucson for a week when it was 115 degrees every day, and the equipment survived. But in terms of seeing and image stability, you really can't do anything about that. The wavelet filtering was an attempt to countermand that, and it worked to some degree.
Mm-hmm.
Okay, great. So again,
there was a follow-up about wanting to know whether it would be affected if you were in the vicinity of a body of water or trying to observe over a body of water in a heat wave.
Oh yeah, that's perfect. And so I started my career at the Big Bear Solar Observatory. I'm sure many of you are aware of that location, which is out on the lake. And yes, that's the ideal situation where you can be over a body of water that keeps the atmosphere really stable and prevents convective upflows that a parking lot would. You don't want to be in the middle of a parking lot, for instance. So not too many bodies of water, I guess, in Egypt or Saudi Arabia, but that would be the ideal situation.
Mm-hmm. Yeah. Thank you. I think that's all the questions we have here.
Okay, great. So that covers all the questions as well. So again, Matt, thank you very much for a great presentation, and I hope we get a lot of OCA involved in the project, in the future project as well. Best of luck to you. And I would like to thank all the audience for their participation. And you would also need to know that you could find out information about this talk and all the future talks on our website at ocastronomers.org. On the calendar section, I'll put that contact information. So best of luck to everybody, and bye-bye.